move seamlessly through. So Mark, I think most of us have seen him. He's one of our rock stars around here, and he's more than 20 years of experience of integrating and leveraging machine learning. He's Senior Director, Data Science and Machine Learning at Oracle, and we're always very pleased to have you here. The one thing you thought you'd got away with, but I didn't get a new fun fact for you today, Mark. You have to give us something new.
You didn't. I thought I responded to your email, Roger, on that one. But, well, so a fun fact, I guess, has to do with I enjoy cooking various types of things. I mean, some of the things that I've made, I look for the most interesting cover on some of the cooking magazines and say, that's a really cool chocolate berry cake, and I want to see if I can reproduce that. And so that's what I've gone through, and my wife and I enjoy doing those types of things, or just making, other types of interesting soups and breads, even a focaccia with sun-dried tomatoes or fresh, what do we have? Sage and rosemary from the garden. It's just perfect.
I have not eaten yet. That is not fun. Don't do that. I'm drooling. All right. Well, thank you, Mark. Thank you for that. And apologies if I missed your email, sir.
Oh, no problem.
With that, we'll leave you to it. I think Kerry was busy trying to get your poll in place. We'll get confirmation from her, but we'll just take it as it comes. So, thank you for joining us today, as always, and I'll leave the floor to you, sir.
All right. Thank you very much, Roger. Let me share my screen. Advance this. All right. Can you see my screen?
Yes, sir. We got you.
Yep.
All right. Excellent. So, invoking user-defined functions from open source environments like Python and R, can introduce added complexity for solution deployment. And, the embedded execution capabilities found in OML4Py and OML4R can significantly simplify this. So today we're going to focus on how to use SQL to invoke your user-defined Python functions with Oracle Database and Oracle Autonomous Database. But embedded Python executions also support embarrassingly parallel use cases, such as scoring data at scale using third-party models. We'll say more about that. Now, so in this session, you'll learn about ways to invoke and use your Python UDFs from SQL with Oracle Machine Learning for Python. So as Roger introduced, I'm Mark Hornick with Oracle Machine Learning Product Management, and thanks for joining me to learn about this powerful capability. So for our agenda, we'll start with a brief overview of Oracle Machine Learning for Python, and then focus on embedded execution through a few examples. We'll discuss the available APIs and specific functions, and then finish up with a demo and Q&A. But I'd like to start with a poll. Is our poll ready? That is the question. And the poll is, which of the following statements best describes your familiarity with OML4Py embedded Python execution? Our options are, I've used or experimented with one or more of the interfaces. I understand what it does, but haven't tried to use it yet. I could use a better understanding of the basics, or I'm completely new to embedded execution. So with the poll open, if you would please let us know how this works for you. And I'm not seeing the actual results here. Oh, there we go. All right, so we have folks I've experimented with or used it. At least 25% of the folks have responded in that regard. Understand what it does, but haven't tried to use EPE yet, about 20%. Could use a better understanding of the basics, another quarter of our attendees, and I'm completely new, so about a third are completely new. Well, this is great. This should help get you introduced to this topic quite well. So let's move on to a brief introduction of OML4Py, just to set the stage. So Oracle Machine Learning empowers data scientists with open source Python by leveraging the database as a high-performance computing environment. Database tables and views are accessed through data frame proxy objects with overloaded functionality that produces SQL transparently behind the scenes. So the in-database machine learning algorithms are exposed through a well-integrated Python API. And as we alluded to a moment ago, users can create user-defined Python functions, or UDFs, and manage them in the database. We're going to be using that term UDF a great deal in this presentation. So Python objects can also be stored and managed directly in the database, avoiding the need to manage flat files. And these UDFs can be invoked from Python, of course, but also SQL and REST, depending on the platform. And OML4Py also introduces support for automated machine learning. So now OML's Python interface is characterized by 4 functional areas. Using proxy objects, the transparency layer allows users to operate on database data using familiar Python syntax, overloading functions that construct SQL for in-database processing. The in-database algorithms are exposed through natural Python interfaces that produce first-class in-database models, enabling scalable model building and scoring. And through embedded execution, user-defined functions can be invoked on database environment spawned and controlled Python engines. Embedded Python execution enables invoking a UDF as a one-off invocation, but it also enables system-provided data parallel and task parallel processing. For example, an open source model can be scaled to large volumes of data for making predictions by requesting that multiple engines be spawned to process chunks of data in parallel. OML provides the supporting infrastructure to simplify and automate this process. So OML4Py supports AutoML, which I've mentioned, and this includes automated algorithm and feature selection as well as model tuning. But in addition to AutoML, we have model explainability, which provides model agnostic identification of important features impacting model predictions. So, you might say, why did we put this feature called embedded Python execution into OML4Py? Well, one thing is it simplifies deployment. Another, it enhances performance and scalability, while at the same time enabling the use of third-party packages and maintaining security. So for simplified deployment in applications and dashboards, users can run UDFs in Python engines spawned and managed by Oracle Database. They can schedule UDFs to run as a one-off invocation or on a recurring schedule using the database scheduler. And they can invoke UDFs not only from Python, but directly from SQL, as we'll see here, and return structured and image results via Oracle tables, XML, and JSON. And this enables a wider range of applications and dashboards to leverage the results. Now, regarding performance and scalability, embedded execution uses memory and compute resources of database environment, not the user's client Python engine. And it eliminates extracting and loading data to the user's client Python engine. Further, it eliminates writeback of results to the database from the user's client Python engine, and can run UDFs to take advantage of system-provided data parallelism and task parallelism. So you can use third-party packages in UDF to augment functionality native to OML4Py and Oracle Database. So these packages include those that might be installed explicitly by the user on Oracle Database instances, or those provided with OML4Py with Autonomous Database. And note that our roadmap for 2022 includes enabling user installed packages as well, a much requested feature. So on the security front, securely store and manage user-defined Python functions in the database as opposed to flat files. You can also securely store and manage Python objects directly in the database instead of dealing with flat files. And of course, data doesn't need to leave the database environment. So let's turn our attention to the APIs. Embedded Python execution interfaces come in three flavors: Python, SQL, and REST. And the Python interface is primarily used for development and testing of user-defined functions. And once ready for deployment, UDFs can be stored in the database script repository for handoff to IT and developers to use from perhaps the other two interfaces, SQL and REST. The SQL API is used, as you might imagine, for deploying Python UDFs in SQL-based applications. And as we'll discuss, there are several ways to interact with embedded Python execution from SQL. One of the other benefits of using SQL is the ability to schedule Python functions to run using database environment resources and the database DBMS scheduler package. The REST interface allows for deploying Python UDFs using REST endpoints, also leveraging database environment resources. So in today's session, we're focusing on the SQL API, but I refer you to our documentation for more information on the REST and Python interfaces. So how can I access embedded Python execution? Well, if you're on autonomous database, we can use OML notebooks or the universal client with various Python IDEs. The SQL API can also be used through OML notebooks or other SQL IDEs like SQL Developer. The REST API is available only for autonomous database shared and can be accessed via perhaps curl or Postman or any other REST invocation interface. Now with Oracle Database, the Python API is available using the universal client with various Python IDEs. And the SQL API, of course, can be used through SQL Developer or other SQL client IDEs. We should note that OML4Py can be used on 19C and 21C databases in the Linux environment. So what are some typical use cases for embedded Python execution? So, we alluded to some of these earlier, but I just want to spend a little bit more time on this so it's clear, what you can get from this functionality. The first one is scoring data at scale. And many third-party packages, such as scikit-learn, don't take advantage of parallel processing, even for scoring, which can be viewed as one of those embarrassingly parallel scenarios that are trivial to achieve, but can involve some additional work to make robust. In addition, you may want to access results dynamically as part of queries, or efficiently materialize results in the database. Another use involves automation, where we want to use a single user-defined function, perhaps to build multiple machine learning models using different algorithms, and do this with system-provided parallelism. A use case that benefits from automation and system support involves partitioned data computations, where we're able to build models, compute statistics or metrics, or even generate plots on individual partitions of data in parallel. So for example, we may want to do this on a per customer or per region basis. The database environment is responsible for spawning Python engines, loading the UDF, this user-defined function, as well as any specified data to the Python engines, and then provide requested results. Finally, the Python engines are released to be reused and reclaimed by the system. Other use cases include simulations, such as Monte Carlo. In this use case, the UDF may actually generate data based on a random seed, or select data using the transparency layer. And as we'll discuss later, each invocation in this scenario would receive a unique index that could serve as the random seed. So let's go to our next poll, and this is about use cases. Which use cases do you find compelling for embedded Python execution? Automating the running of my Python UDFs in engines spawned by the database environment? Taking advantage of system-provided data parallelism and task parallelism? Perhaps it's using a native Python machine learning model to score large volume data, generating image plots and returning them from SQL, or running Monte Carlo type simulations. And if you have something else in mind, feel free to specify that in the chat. So our poll is open, and we'll give it a few seconds here for people to respond. And then if you can share the results, we'll see what users had to say. Okay, so automating the running of my Python UDF in engine spawned by the database. Almost 2/3 are interested in that. Taking advantage of system-provided data parallelism, about 40% there. Again, 2/3 for using native Python ML model to score large volume data. Yeah, that's a very popular one. And even simulations for Monte Carlo got 40%. And 1/4 are interested in generating image plots from UDF and returning them via SQL. So great, thank you very much for that feedback. So what do these user-defined Python functions look like? They can include just about anything. Here are a few examples, from building machine learning models and computing statistics to scoring data using native Python models and generating images, plots, and charts. So we've talked about embarrassingly parallel processing, but what do we mean by that? Just to be clear, here's an example. The embarrassing aspect is because it's so easy in concept, and with adequate system support, can even be easy in practice. So we start with data in the database, and this consists of rows that we want to process using a user-defined function. We can partition data in 2 ways. In chunks, n at a time, where we don't care about the grouping, or we can partition data using the values in 1 or more columns, for example, by region, customer, or type of equipment. We next need to start a Python engine, or more if we want parallelism, and then load the UDF in each Python engine to invoke the UDF with its partition of data. Now, if we have too few Python engines relative to the number of partitions, we simply round robin the invocations to reuse Python engines until all partitions are processed. And finally, we may want to store the results back in the database. So this is what we mean by embarrassingly parallel. This entire process occurs within the database environment. We don't need to pull data to the client Python engine to make this happen. Now, for the examples that follow, there are 2 concepts I want to introduce now. And the first is that of the Datastore. A Datastore allows users to save Python objects, including OML4Py proxy objects, in the database as a named entity, and load them back into Python memory across Python and database sessions. And data stores are also used with embedded Python execution for passing non-scalar arguments, like Python machine learning model objects, to user-defined functions, especially for the REST and SQL APIs. So a data store can contain multiple Python objects, making it very convenient for passing data to these user-defined functions. You see here that OML save and load are the 2 main functions for saving to and loading objects from the database data store. Here's a summary of the functions available to manage data stores. There's, of course, the save and load we've already mentioned, but you can also list the data stores, see the contents of an individual data store. These can be from Python, but also directly in SQL queries using the views that are shown here. And of course, you can delete data store instances or objects within a given data store instance. So it gives you a rather complete way of manipulating Python objects within the database environment. The second concept is the script repository. And this is a table that contains UDFs stored by users. Storing the user-defined functions in the script repository is required to use embedded execution from SQL or REST interfaces. And these UDFs are typically used for embedded execution, but they can also be directly loaded into the client Python engine, or even another UDF, which enables sharing code easily across your user-defined functions. Now, storing these in the database enables leveraging database security with access privileges for sharing UDFs among users. So with this as our foundation, let's walk through an example showing the OML4Py SQL API to build a model. On the left, we have a UDF that builds a linear model from scikit-learn, then saves this model in the database using the data store, and returns the model a string. As shown here, this function can be stored in the database Python script repository using the PyQScript function with the name myLinearRegressionModel. And note there is a corresponding Python API for storing UDFs in the script repository as well. Now on the right, we show invoking this Python function from SQL using table apply functionality with the SQL function PyQTableEval. This is actually a table function, and the system will automatically populate the first argument of your user-defined function dat with the specified data from, in this case, the iris dataset, and it'll provide it as a pandas data frame. So we pass in the iris table name, the user-defined function parameter list, which includes the model name, as well as the Datastore name that we want to use to store our model in the database as. And we specify the output as XML and the name of the function as stored in the Python script repository. So running this statement results in a Python engine being automatically spawned, the function loaded, and the table data loaded as a pandas data frame in the first argument dat. When it's finished, you have a native Python model stored in the database, ready to be used by another Python user, or an embedded execution invocation like RowApply, which enables the use of these system-supported data parallelism capabilities. On the bottom right, we see the output after invoking the function, which is simply the value returned from this str function invoked on the model. And it has the value linear regression provided as an XML string. But how did we get here? It seems like that's a nice result, but did we have to go through a process? Well, one process you consider as a best practice for developing embedded execution UDFs. And this is kind of a 10,000-foot view of the workflow we recommend for developing such solutions with embedded execution. We start with developing a script directly in the Python engine. Likely using the command line with tools to support Python debugging and understanding your results. Step 2, we wrap this script in a user-defined function and run it using one of the embedded execution functions from the Python API. And we'll review more of these shortly. And this allows us to ensure we have the proper inputs and outputs to our function, at least from the Python perspective. Now, step 3, if we're deploying this solution through SQL or even REST, we need to ensure that the inputs and outputs are in a form needed by those interfaces and match their requirements. This may include having non-scalar inputs and Python objects stored in the Datastore, or using special control arguments for images. In step 4, we create the UDF in the script repository in the database, which can be done using the Python or SQL APIs. And finally, in step 5, we run and validate the UDF using embedded Python execution, a SQL API, in a select statement. So at this point, you're ready to provide the SQL to solution developers for use in enterprise systems, applications, and dashboards. So with the model already created, let's define a function that uses that model to make predictions. In this case, the predictions are about the petal width using the iris dataset. We're returning the predictions along with the corresponding species and petal length predictor values. The OML script create invocation is what stores the UDF in the database script repository. And by convention, we're using the same score mod to identify the function in the script repository, passing the UDF itself. The additional arguments indicate that we're not planning to share this function with other users and to overwrite the entry if the function already exists. Now in this example, we're taking the same user-defined function, but storing it in the database using the SQL API via the PyQScript procedure, which we saw earlier. Python developers and data scientists can provide Python UDFs to their SQL user counterparts for storage in the database, or they can hand them off directly to the database themselves. Then they just provide the name of the function in the script repository to developers using SQL or REST. So how might we use this user-defined function? Well, let's answer this with the OML4Py function RowApply. We start by getting a proxy object to the iris table that we already have stored in the database as a table. We provide this proxy object to the RowApply function. And notice that we're passing in the Python function object directly here. But we could also provide the function name as it exists in the script repository. We're asking for 10 rows of our data set to be processed at a time, and to do this in parallel using multiple Python engines. Note that such functionality is available both on Oracle Database and Autonomous Database. Now here's the corresponding SQL invocation using PyQ Roweval. You'll see some familiar parameters from the previous example. We have the data iris, what the output should look like, specified as a JSON string, the number of rows to feed each invocation, 10, and the name of the UDF in the script repository, again, scoremod, but as a string. The second argument to Roweval is the parameter list. It's also a JSON string and specifies that the input is a pandas data frame, that we want parallelism, and since this is on Autonomous Database, we want to use the medium service level to provide parallel compute resources. So let's take a poll at this point about language interfaces. Which of the OML4Py embedded Python execution APIs do you think will be most useful in your organization? The SQL, the REST, or Python APIs? And you feel free to select all that apply. And if you have something else in mind, let us know that too. And the results are in. We have certainly 2/3 of our audience is interested in SQL. Of course, 71%, I would not be surprised by that, is for Python. And REST is about 1/3 of our users. So that is very good to see. Thank you for participating in that poll. And I happen to see 2 questions in the Q&A, so maybe I'll look at those right now. When will OML4R be available? Well, there are 2 answers to that. OML4R is available today. It's available for the on-premises and database cloud services platforms, and on Autonomous Database that will be later this calendar year. And then, can machine learning be used on a tabular response from an embedded SparkQL query via a SEM match clause? That's something I would have to look into. I don't have an answer for you for that right now, but I will take that. And if you drop me an email at mark.hornick@oracle.com, I will be happy to get back to you on that particular question. All right, but let's continue now. So far, we've seen the table eval and RowApply functions in our examples. Here's the complete rundown. I'll just refer to the SQL functions here. If you don't want data automatically loaded into your function, you can simply use the PyQ eval function. To have the full data set loaded at once for your UDF to process, you would use the PyQ table eval. And if you're building a model, a single model, this would probably be the one you would use. Although you should keep in mind that your Python functions and the Python engine need to be able to handle the size of the data of this table. And this is not automatically scalable, because if you're using a Python third-party package, for example, you do have to make sure that the Python engine could naturally handle that. So this applies not only to table eval, but also to all the functions where data or objects are loaded into the Python engine. Now, if you want to run your UDF on chunks of data, you use PyQ Roweval, as we saw earlier. And if you want to run your UDF on data partitioned by values in one or more columns, you'd use PyQ Group Eval. If you want to have your UDF be run just multiple times, this is where you would consider index eval. This last function requires a little bit more comment. With index eval, each time the UDF runs, its first argument receives the index number of its invocation. And this allows you to use that number as a random seed, or to generate a random seed, or to select different behaviors within the function. For example, when building models using different algorithms on the same data. Each index value may indicate a different algorithm to use. And the UDF can return a variety of Python object values as listed here. Now, an added feature of embedded execution on autonomous database is the ability to have asynchronous behavior. In this case, using the SQL or REST APIs, you can kick off a job to run and then check its status, and when completed, retrieve the result from your UDF, what it produced. And we'll see an example of this in the demonstration. Before shifting to the demonstration, though, we should highlight a few differences between the embedded SQL API on autonomous database and Oracle database, which includes on-premises and DBCS and other cloud deployments. The most notable difference is the ability to custom install third-party packages. With Oracle Database, users with root access to the database server machine can install the packages they want to use directly with embedded Python execution. And this is a roadmap item for autonomous database to be included later this year, where users will be able to custom install packages. Regarding authentication, on autonomous database, authentication is token-based. And while on Oracle Database, we use the standard username and password login, you can also use the Oracle Wallet there. Asynchronous jobs and specifying the service level of high, medium, and low to control parallelism are unique to autonomous database. Now, parallelism on autonomous database is achieved using Python engines in VM-supported containers managed by the autonomous database environment. And here, the service level determines the number of parallel engines. For Oracle Database, we use the XProc, or what's these external process mechanism, for Python engines. These can run directly on the database server machine. So it's important to realize that embedded execution doesn't magically make third-party packages scalable or performant, modulo the embarrassingly parallel capability we talked about. The characteristics of the underlying packages, just to reiterate, remain, and this needs to be factored in when designing UDFs and solutions in general. So with that, let's transition to the demonstration. Let's see, is this the, I think this is it. All right. So this is the Oracle Machine Learning Notebooks environment, and I'm just starting up the notebook server, where we'll take a look at the flow of using the SQL API as well as the Python API for embedded execution. All right, so let's just scroll down a little bit here. And what we see is the first thing that we need to do if we want to use embedded execution in the autonomous database environment is we need to add the user schema to an access control list. And that's just showing how you would do that here using the exec capability through an OML notebook SQL paragraph. And the same thing is we can then verify that the access control list is properly set by doing the PyQ get host ACE. But that's some of the details to set things up. The key thing is we need an authentication token. And this authentication token is one that goes against the autonomous database. And we've defined a convenience function here that does this for you, but we're simply going to invoke it and then set the authentication token. I'm going to make this just a little bit larger so that it's easier to see. And we're pulling out our access details, the URL, the username and password, which we're using for our get token to function. And then we're setting the authentication token. And now we're ready to go to use this in the rest of our example. All right. First thing that we're going to do is look at the data that we'll have in our examples. And one of these is the iris table. And this is a standard OML4Py process. We're just pulling out the iris data from scikit-learn data sets, and then we're creating that as a table in the database using OML create. If you've seen demonstrations of OML4Py in the past, there's nothing unusual about this. It is the same from that. So we can just run that again, and this will start up the Python backend engine and then provide the data for us as a database table. Now, the next thing is, let's create a simple user-defined function and save it to the Python script repository in the database. We have a simple count function. And all this does is say, how many rows are there that are provided to this function? So we're going to store that in our, or just create that function called group count. And let's invoke it. This is pure Python. There's nothing elaborate about this. And we see that we're asking for how many Setosa rows do we have? And we see that there are 50. This data set has a total of 150 rows, and there are 50 of each type of flower. So that's the answer we expect. Now, let's use the RowApply function to say, well, I want to partition the data on the species, and then I want to invoke this function in parallel on each subset, each partition of the data grouped by species. So we pass in the iris data. Our index is the species column, and then our function is the group count defined up above. And the result we want to get back is the species and count. So running this has just gone behind the scenes to create multiple Python engines. It has loaded the data into each invocation of our group count function and returned the result here for us to work with. That's pretty straightforward. So let's say that we want to do this using the SQL API. Well, the first thing that we're going to do is store our group count function in the script repository. We create this as a string here, as you see, and then we're going to invoke the script create group count, passing in that string, and if it's already there, we're simply going to overwrite that. So that goes in, done. Let's look at the script repository. So if we go to OML script dir, we'll see that we've just loaded this here. We're about time, and we have that function available. Next, we're going to run this function through the SQL API using the PyQ group eval. This is what the SQL would look like. Taking our iris data, that our input type is a pandas data frame. We want parallelism. The service level is medium, which allows us to have parallelism. Our output format consists of these two columns. We're grouping it by species, don't care about the ordering. And we're going to use our function in the script repository group count. So this goes off and spawns our engines, produces the result, and brings it back through SQL as a row set that we can simply access later and combine with other results there, or materialize it if we would like to have it be persistent. And we can make this asynchronous as well. So we can invoke the PyQ group eval asynchronously. And in this case, we will, the key thing here is to set this async flag to true. By doing that, it means that we're simply going to create the job, and then later we can see what the job ID is. We're going to pull that out from the result, and we see the job ID. And we can then use that job ID to actually retrieve our results when it's finished. So I have a sleep in here, just guarantees that I have a few seconds that allow the asynchronous job to complete. And then we're going to pull out the result. We check the status, and by checking the status, it gives us a job URL, which indicates that it is indeed complete. And then we can pull out the result. And in this case from SQL, we're doing exactly that, getting the job result, and we see the JSON string with that available for us to use. Now, we can also build a scikit-learn Python model using embedded Python execution. Here's an example that does exactly that, and we're saving this to the Datastore that we mentioned in the discussion earlier. So let's save that. We're going to add that to our script repository. We can use the table apply function to build the model, and our function is actually returning the coefficients of the model that were produced. And it's storing that model in the data store named DS1. Now we can view the data store contents because we've said, yeah, this actually exists there. And in DS1, we have our regression model, a linear regression model. We can also access that from the SQL view that you see here. So we have parity between both SQL and Python. And we return output as a structured table if we invoke that same function, buildLM, from SQL. Here we're passing in the iris data. We have our parameter list. We want to save our model in DS2 this time, and we're going to be getting back our results, and that's the definition of that. So again, we're spawning a Python engine in the background, passing in the data with the user-defined function, and we see the results coming back there. And just to prove the point that we're looking at DS2, and we can see the results that are in there. We did indeed create another model. Now we can do the same thing from JSON. We have that. We can create an XML string that for the result to come back there for different use cases. And then let's just move on to scoring that uses the system-supported data parallelism. So in this case, we have a function called scoreMod. We're going to load the model that we created earlier, and we're going to use it to predict results, and we're going to provide those results back. So let's take this function and store it in the script repository. And then use RowApply, as we talked about earlier, to get this processed in parallel. We'll use the iris dataset. We pass in our function. We're going to use the model produced that we stored in DS1, our data store. We have 50 rows we want to process at a time, so that will give us 3 invocations, and we want parallelism. So we're doing this from the Python API, and we see the results from that, but we can do the same thing from SQL. In this case, iris, our function scoreMod, we're doing 50 rows at a time, and we get the result back as a row set from the SQL query. So it just shows how easy it is to go back and forth between Python and SQL and leverage your your Python functions in this context. One other thing I should highlight is that you can also have images come back as PNG images. So this is a very trivial function that just does a density plot on some data. And so we'll create that function, store it in the script repository, and we're going to invoke that using table apply through the Python interface. And this allows us to see the image that was produced comes right back in the notebook environment. Now you can do something similar with this in SQL, and this would be the invocation here. We're just turning on the graphics flag to true. This isn't something that's enabled currently in the notebook environment, but from the SQL environment, you would get back a table that corresponds to each of those images, and you can run from there. All right, so that's the end of our demonstration. Let's just continue on then with wrapping up with some information that you might find useful. Here are a few resources. You could check out our blogs located at the link here. And for additional SQL, Python, and R code and notebook examples, check out our GitHub repository. You can see the OML office hour sessions, perhaps sign up to get notifications of future events, and also check out the documentation here for your reference. We also have the OML on Autonomous Database Specialist certification and a series of Oracle Learning subscription content that can help you prepare for that certification. And to quickly try out OML capabilities, consider using Oracle Live Labs, which allow you to quickly spin up a database instance with step-by-step instructions for workshops involving OML components, such as OML4Py, as we've discussed here. So with that, thank you for joining this session. And if there are any additional questions, I'm happy to take them.
Thank you so much, Mark. We have one from Phil Canetta. How much of this technology is being used in an HPC environment?
How much of this technology is being used in an... Well, I guess what we're doing is we're leveraging the database as the high performance computing environment. So any place that so the transparency layer, for example, the transparency layer is one that is saying, I have a proxy object to tables in the database, Python data frame proxy objects. And I can invoke overloaded pandas data frame functions like merge, or there are others that we've overloaded as well. And that translates that into SQL so that it can be run in the database as leveraging the database as a high performance computing environment. Now, for the embedded execution, the whole purpose of that is to allow us to run Python functions, these user-defined Python functions, as we've been talking about, in Python engines, because we may be leveraging third-party packages as well to support that, like scikit-learn. And in that case, we have perhaps multiple Python engines that are being spawned. That's not in the kernel of the database. Those engines on autonomous database are run in VMs, or on premises, they're being run as external processes on the database server machine. And I should mention, just with the in-database machine learning algorithms, those are also leveraging the database as a high-performance compute engine, because those models are actually in the kernel of the database. And so we're just exposing those through a Python API. So there are a couple of ways to answer that question. I hope that addresses it.
Thank you so much, Mark. And thank you for your session. Amazing as always. Thank you so much.
My pleasure.
Thank you. So yeah, I think it's a wrap basically. We just wanted to first of all thank you, Mark. Really enjoyed that, as usual, like drinking from a fire hose when you speak.